And welcome to Chapter 19, where we're going to be talking about acids, bases, and salts. And when we're dealing with salts, it's the acid-base properties of those salts. In this first section, 19-1, we're going to be talking about the various theories on acids and bases, and just kind of give you a flavor on where this chapter is going. So the first thing that we want to discuss are what are some of the properties of acids and bases. Now, acids and bases have been studied for well over a century now, and some of the early properties that they observed with these acids and bases, well, starting with the acids, acids are substances that will generally taste sour, believe it or not. Now, we don't use the taste test in the laboratory anymore because of the adverse effects that it can have by ingesting some of this stuff, but you actually know that acids taste sour. If you think of citric acid from oranges and lemons, you know that they taste sour. But all acids are going to be that way. Vinegar is another example. It's acetic acid. That also tastes sour. In addition, the acids will change the color of an acid-base indicator, and that really depends on how much acid that is being added, but it can change the color of an acid-base indicator. And it can be either a strong or a weak electrolyte. Now, it is going to be an electrolyte, but exactly if it's going to be a strong or a weak, it depends on the nature of the acid. Now, bases, on the other hand, bases actually taste bitter. Soap, shampoos, those are bases. And so if you've ever obviously gotten those in your mouth while you're taking a shower, you'll know that that is in fact the case. The bases also change the color of an acid-base indicator. And also, just like the acids, can either be a strong or a weak electrolyte. All right. So those are just some basic properties of acids and bases that you should know. We'll get into more details on some of the specifics of acids and bases here as we go. So now, one of the first definitions of an acid and a base was developed by a guy by the name of Svante Arrhenius. He was it was back in the late 1800s, where he was developing his definitions of acids and bases. He was studying them basically with their conductivity. But what he said was that an acid is a substance that can produce protons, and we mean by protons hydrogen ions, in water. For example, when you put, say, acetic acid, which is CH2H3O2, when you put that into water, what's going to happen is that it's going to produce, this hydrogen is going to be released, and it will be free as a proton. All right, we're going to tell you what that's going to look like in some of the reactions here upcoming shortly, but the basic idea is that it will produce protons when you put it into water. Now, when we talk about releasing protons, they come off one at a time. If you take a look at hydrochloric acid, HCl, when you put it into water, you're going to form hydrogen ions and chloride ions. That's what conducts the electricity, which is why hydrochloric acid is an electrolyte. In fact, it's a strong electrolyte. When we put sulfuric acid into water, though both of these hydrogens come off, we treat them as if they come off one at a time, so you'll be left with the hydrogen sulfate ion, HSO4-. Similarly, when you put phosphoric acid in, it will also produce a hydrogen ion, and you'll be left with a dihydrogen phosphate ion. It'll look something like that. Oops, that should be just a 1 minus, not a 2 minus. There we go. All right. So that's what an Arrhenius acid is. Now, an Arrhenius base. A base is going to be a substance that produces hydroxides in water. For example, if you take, say, sodium hydroxide, when you put that into water, you get sodium ions, and you also get hydroxide ions. They simply dissociate, and voila, you have your hydroxide ion. Any metal hydroxide would be an Arrhenius base. And so now, if you take a look at an Arrhenius acid-base reaction, you can take your, let's say, hydrochloric acid, which is going to produce the hydrogen when you put it into water, and you can add that with, say, your sodium hydroxide, which will be our Arrhenius base, and that's going to form, when this produces the hydrogen ion and this produces the hydroxide ion, the hydrogen and the hydroxide come together to form water, H2O, and the sodium and the chloride come together to form NaCl, salt. So that would be an Arrhenius acid-base reaction. It would look something like that. Now, that is not the only definition of an acid or a base. That was developed in the late 1800s. Later on, two guys independently, Bronsted and Lowry, came up with definitions of acids and bases that simply expanded that definition. So what they said is that an acid, not only can it produce the hydrogen, but it will donate hydrogen ions, whereas the bases will accept the hydrogen ion. Now here's the deal. A Bronsted-Lowry acid-base definition is simply broader than the Arrhenius definition. It's kind of like the difference between a rectangle and a square. Okay, the square is very specific. That's the Arrhenius definition. The rectangle is going to be a broader definition. All Arrhenius acids and bases will be Bronsted-Lowry acids and bases, but it's not necessarily the other way. Similarly, all squares are rectangles, but not all rectangles are squares. All right, and here's where a Bronsted-Lowry definition can differ from the Arrhenius definition. If you take a look at the reaction between hydrogen chloride gas and ammonia gas, notice we're not putting anything into water here, so automatically we're not thinking Arrhenius acid base. There's no water for the hydrogen to be produced in. There's no water for a hydroxide to be produced in. But what's going to happen is that the hydrogen is going to be donated over to the ammonia from the HCl. So because that's doing the donating, this would be considered an acid. Because the ammonia is accepting the hydrogen, it would be considered a base. And what happens is that the ammonia becomes ammonium with a positive charge. What's left of the HCl is just the Cl minus with a negative charge. The positive NH4 and the negative Cl come together to form a solid. It's a kind of a white solid that looks like a smoke when you put it in when the reaction takes place in the atmosphere. All right. So you have these two definitions, the Arrhenius definition and the Bronsted-Lowry definition. You're going to need to know both, just realizing that the Arrhenius definition is more specific. The Bronsted-Lowry definition is a little bit broader. Every Arrhenius acid base, acid and base, is a Bronsted-Lowry acid and base. For example, we've already mentioned that HCl is both an Arrhenius definition and a Bronsted-Lowry definition. Sodium hydroxide, NaOH, the hydroxide can accept the hydrogen. However, there's a lot more compounds out there that can accept hydrogen other than just the hydroxide ion, such as ammonia and many, many others. Okay? All right, so that's the first part of 19-1. In the next podcast, we're going to take a look at conjugate acid-base pairs.